Let me tell you first now about this story, the history of this project, and this starts with the MSO technology. Most probably you all know the MSO concept and technology. I will give you a short example about the MSO technology, maybe not to you, but for somebody who is listening this broadcast and not familiar with this MSO technology. And EU Medicine, our network, basic network, EU Medicine, and how EU Medicine organized this MSO for SZE project. So the MSO is an abbreviation for the mathematical modeling, simulation, and optimization. This is a key technology in the most sectors of the industry. We all know. The M is for mathematical modeling. Modeling translates a challenge of the real life into a mathematical problem, and also provides an algorithm for the solution. And if we have already an algorithm which will approximate the mathematical challenge, then we shall have an implementation on a computer to make a simulation. The simulation implements the algorithm which is coming from the mathematical methods. And in the simulation, we run this algorithm on computers and evaluate the results. We can show a lot of details more from the simulations, if it is properly set, than from many experiments. So here, the evaluate we can compute some indicators, we can generate some maps, so visualize the results. And the optimization finds the best design, roughly speaking. This MSO technology is a close interaction with data processing. So a lot of time we are provided also not only the problem but also measurements. And these data processing, sometimes they are called digital twins. The MSO and the data processing has to be handled together, and the computing part, the simulation part, is often connected to HPC, high performance computing. Let me show you one example, and the part of this example is also pilot of this project, of the MSO for SZE project. The challenge is that the nitrogen oxides level is rather high in several cities. So people suffer from fresh air, and its policymaker asked whether it can be organized so the traffic or some other parameters so that the NOx concentration became smaller. And they can measure it, but proper measurement stations are very expensive, and only few can be put to a city. And therefore, modeling and simulation of this system is natural. So here on the map, you can see a part of the city of Győr of 130,000 inhabitants, and also you can see already after the simulation of the wind flow and also the concentration. And you can see a red spot area here, where the average, where the concentration of the NOx is much higher than the average. And up to now, the policy is set to the average. And people living very close to the maximum suffer a lot from this high concentration of the NOx. So we need some simulation tool because with measurements, all the hotspots cannot be measured. With simulation, we try to capture all of them. And for that, we set up a simulation and optimization framework and with some databases for the traffic and the meteorology and the city databases. We set up a simulation method, simulation part, which needs pre-processing. And then if it is already prepared, the simulation, we set up the initial conditions for the design parameters, which are traffic signal parameters. We simulate the traffic, then the emission, and after the emission, the dispersion. If you need accurate dispersion, then you need big computers or good softwares. And this was done by a commercial software. And this simulation was verified. Some pictures from the typical work for the mathematical modeling, simulation, and optimization, modeling the geometry, meshing, fitting the two components of the simulation together, the traffic geometry and the mesh, computational mesh of the airflow. We have meteorology data, and from all of these, we can compose the simulation in the city. And we get the results from the simulations, the hotspot areas, and we can compute the indicators. Other end, this coupling of the simulation and optimization is a very straightforward coupling. More sophisticated techniques can be used as well. For example, model order reduction techniques, or using some other tools from the so-called digital twins methods, from data processing and also from the simulation. In general, the algorithms, we have to notice one point here. In general, the algorithms develop much faster than hardware. So it's not enough to say that if we want to have a more efficient computation, then we have to get a better computer, buy a better computer. It is already proved in many areas of the science and technology that in particular in that case, which is projected some numbers about that, that for linear optimization, it was measured that on a rather long period, it was measured the algorithm development and also the hardware development. And during those years, LP, linear programming solvers, the solver algorithm has been very improved 303,000 times. And the softwares and the hardware has been developed 1,600 times. So in total, these bring the multiplication of these numbers, give actually the speed up of LP solvers on new, that time new hardware and with new algorithms. And this shows that 1 minute calculation, 1 second calculation at the oldest time was, after the development of the software and the hardware both, 1 minute in the new time was 2 months in the old time. But to achieve that great achievement, we need also the algorithm part to be developed. EU medicine, and it is in the industry, it is recognized that mathematics brings a lot of improvement in simulations and in the innovation, but it is not reflected back enough in the policymakers level. Therefore, mathematicians established the EU MedSyn, the European Service Network of Mathematics in Industry and Innovations, and this is a network of networks. The national networks, you can see the countries belonging to this network on the map. And these national networks represent the entire community in those countries they are from. And this is becoming a big network with mission leverage the impact of mathematics on innovations and to be a dedicated one-stop shop for mathematical services, and to be able to provide a dedicated one-stop shop for the industry, we have to build an infrastructure for the mathematical services. So this is the point where our project started. We had in EU MedSyn, we had a wish to generate an e-infrastructure, and there was a call, and EU MedSyn composed a consortium from us, here represented from a research group represented here in the workshop, and with experts Atos and HPC expert Atos, and we made a consortium for building this infrastructure. So to build a HPC-oriented cloud infrastructure, from HPC it has a large compute power. From cloud means that we can reach this infrastructure simply, roughly speaking, and to put there advanced mathematical tools, mathematical development frameworks, and also end-user applications for solving societal challenges. And in this workshop, we are to provide information what has been already done in the project, and we would like to introduce these frameworks, the infrastructure, and also the end-user applications in the workshop. This was an introduction of the main framework of the project, and I'd like to ask Javi Nieto to give his lecture.